Hey folks, and welcome back to a new video. So it's been a while since we did kind of a functional programming algorithm type thing, whatever we call this. So I decided to do some programming. There's an algorithm that I want to play around with for a while that I haven't done before. So I decided to scratch that itch while I was sick a couple of weeks ago, and I decided to work a little bit on this function, and now making a video about it. I'm going to show you guys how it works. So today we are looking at the Wavefunction collapse algorithm. So Wavefunction collapse, if you came here through a thread of researching some physics stuff, some quantum mechanics, this is not the video for you. This will not help you with that. So I'm afraid you may want to click on, well, you can stay and watch this if you want to listen to the algorithm, but that would purely be procrastination if you were trying to learn physics, because I ain't going to teach you about that today. So anyway, with that stated, what is wavefunction collapse? The algorithm, not the quantum physics concept. So the wavefunction collapse algorithm is an algorithm by which we are able to procedurally generate maps and pictures, pretty art, based on taking a set of predefined tiles that all have, kind of geometric structures on them. The key point is that those tiles usually have a limited set on them, and usually they have boundary edges which are compatible and some boundary edges that aren't compatible. So there's only certain ways that you can arrange the tiles that are allowed by your configuration. And what you do is you basically take those tiles, you feed it into an algorithm. The algorithm works on a grid. It processes through what's there and figures out what tiles it should put where to make a cohesive image out of all of your starting ones. So for the example I have here, I'm going to show you the basic set of kind of what we're dealing with. So we have tiles that look like this. So this is basically, it's sort of like a road network type thing is what I have. So we have a tile like this. This is obviously a crossroads, so the dark brown is the road. Then I have like sort of, ditches or, laybys on the side of the road, which are these sort of yellow. And then the green is grass, I suppose. So there's a bunch of different kinds of these. This is a crossroad. We have here a vertical road, which obviously has grass either side of it, and then a straight road running through it. And then aside from that, I have, got to zoom it in. This is just grass, so this will just be completely empty space on the grid or just a green field. And then there's all sorts of others. There's a horizontal road, and then of course there are corners. So effectively, and there's the 4 different types of corners if you rotate this around. So effectively what we have here is we can create a map or like an image or whatever that is made up of empty space or green space, which is like our green fields, and then roads running through it, and they all run either vertical or horizontal or right angle turns in any direction, and then there's also crossroads. So effectively the goal of what our algorithm is that every time we run it, we're going to get a new, unique, effectively random picture generated using all of these components. So applications for this you can think about for certain video games that have a lot of procedural generation. You could use a system like this to generate the levels. So if you think of like a dungeon crawler or something like maybe Hades, where you've got very set arenas for each thing, but they're configured slightly different for each battle. So you could run an algorithm like this, which can basically piece together the map as it sees fit and generates it procedurally, so that you don't have to have these pre-configured maps. All you need is each of the building blocks, and then you can configure a new map at random for any kind of encounter or anything like that. Obviously, those systems and there are more advanced systems that video games in practice would actually use. This is just a really basic example of an algorithm that you can use. In my opinion, it kind of is just more interesting to see how the art piece can generate out of it, because you can really do some fun stuff with different types of sets of images and stuff like that. So this is our one, really basic, really simple. So the input into this system is all of our images here, which we have. These are all 3x3 images, so they're 9 pixels in total for the whole thing. The way I generated these, they're 9x9. So 81 pixels in total. The way I generated these, I generated them all manually using this pixart.com. They have this little thing generator that lets you create your own pixelized art, and also lets you create GIFs of them, which is kind of cool. You do like pixel animations. So yeah, I just use the free version of it, and just drew these manually by hand. So they're very, very simple to draw, and then I just downloaded exported each one as a PNG, and hence why they're also quite small, because it was just easy to just have to click on a few pixels to draw them. And then in the output, we use these to render a larger GIF in the output, and I scale them in the code, so you don't have to worry too much about the actual size of them. Okay, what else should we say about this before we look at the code? Oh yeah, so the other input, so we have all of our images, that's fine. The other thing that we need to be able to tell our code, and this is really the key about how the algorithm works, is we need to be able to tell the algorithm what squares can go together with what other squares, or what squares can be adjacent to each other. So typically the algorithm works, if you're doing a square grid, you just have to look north, east, south, and west, and you're trying to figure out, well, what square can be adjacent to the north of this square, or what square can be adjacent to the east, south, north, whatever of this square. And a square will be allowed if it has an adjacency rule that both obey. So bear with me a little second. It'll become a little clearer as we go through the algorithm. But for my example, most of the time when people do this in code, they just like hard code out what those adjacency rules are. I created a little config file here, which just has some JSON in it that lets me map out what my adjacency rules are. So I named all my files based on an ASCII character that sort of resembles what they are, which has made it easier in my brain to try and organize this. So these are the keys in here for two different things. Weights. Don't worry too much about weights. I've basically made it so that my algorithm will favor one type of square over another. As you'll see here, the blank square, the dot square, which was my just colored square, is the most favored square in the whole thing. So that means that this algorithm, when it runs for me in practice, will mostly spit out empty space, with the roads being more sparse. And then various other things, weights down here. Crossroads, I don't want so many crossroads. And then various other weights. And you can obviously tune and play with these, and you'll get different kind of outputs of the algorithm. The other main key then is this edges. So this is really the crux about how this whole algorithm works. You need to define those adjacency rules. So I define them as these edges. So I use a basic kind of thing here of it's up, right, down, left. So this is up, right, down, left. So if you have a dot, or a dot, which is an empty blank square, or a field, or green field, it has an empty type edge, which is the blank edge, a green edge, on its north, and its east, and its south, and its west. So they all have the same edge. So then let's look at a crossroads. So a crossroads edges, on its upper edge, it's got, so for the crossroad, its upper edge, it's a vertical edge. And then if you see over here, I happen to have the vertical pixel open in the pixel art window here, you'll see that this edge is a vertical edge, or what I've defined as a vertical edge, and that matches here. The other thing that matches in the crossroad that's also a vertical edge is the bottom edge is also a vertical edge. So you might be certain where I'm going with this now. If you look at the right here, this is a horizontal edge. This is also a horizontal edge. And so as we go through this config file, you'll see all the different shapes. They start to match the types of edges that they have. So for this, the dash, which is a horizontal in mine, you've got an empty edge on its north. You've got an empty edge on its south. And then on its east and west, its left and right, you've got two horizontal edges. I'm not going to talk through the corners because these always break my brain doing the angular rotations, but basically it's just a little truth table, and you map it out with all the configurations, and then you'll see that this applies to each rotation for the corner pieces, the elbow pieces. And that's the real key about this whole algorithm. Making this work is that once you've defined each of your tiles, and once you've defined what their allowed edge connections can be, Everything else is quite simple from there on. You can make this more complicated. So in ours, we don't have a ton of rules about how things can be connected. It's just via these edges. We have these weights that we apply, which I'll show you where they come in, but it's not really a rule as to how things can connect. You could go further into this and you could make more rules. Basically, you're trying to randomly assign like a function that says what can go there. You could make that way more complicated. We haven't done that. We've kept it really simple. So let's have a look at the code, and let's see how this works. I never said off the top, this is implemented in Rust, of course, as would be many of my algorithmic programming stuff that I've done over the last few years. So yeah, let's have a look. Code is pretty simple. We have a config object up here, which we read using a function down here. It's not super interesting, just loads in JSON file and parses out our structure. The main bulk is this main function here, and the actual algorithm itself only takes up, it's less than 80 lines of code. There's a lot of boilerplate and setup up here as well. So first few things that we're doing in the code, loading the config file, set up our tiles. So I also export this so I have two functions here. One that prints a grid, which gives you like an ASCII grid output in the terminal, and another one that creates an actual GIF. So it's rendering PNG frames or image buffer frames in here and then putting them into a GIF. So that actually is quite slow to do as it happens. So you'll see when I run this in a few minutes that the algorithm itself isn't actually that slow, but when you dig into the performance, it's actually generating the GIF that's very slow. There may be a better way to do that. I'm not sure. Not an expert in image processing stuff anyway, and definitely not in Rust. So yeah, if anyone knows a quicker way to do that, let me know. But this is the way I've done it. Basically create a GIF file container, and then we're going to create an image buffer and stick frames into it. So yeah, that's all just set up here. Now the real meat of the algorithm comes up here. We've got a height and width that we've arbitrarily assigned at the start, and we create a grid, which is just a hash map. So it'll be a sparse thing. This won't be sparse. This will be the full grid of everything that we want to see. So it will end up eventually populated with every point that is within the dimensions of this grid between this height and width that we set up here, the variables. So yeah, the other thing we do then is we create this candidates set, which is the set of candidates that we're going to be looping through each time that we want to try and figure out what we need to do here. So the way we do this, we insert into the grid. We're going to seed our grid with one single point. So I've gone to the very center of the map and I've stuck in a crossroad, and then the whole thing expands out from there, basically the whole image. So you have to kind of pick one seed point to start from. What we do then is we get the neighbors that surround that seed point. So there's a function down here that I defined that just loops through all of the neighbors, goes through the directions north, east, south, and west, using this handy little constant defined up here. And it just loops through, checks if they're outside or inside the bounds, and then returns the list of all the neighbors. And those become our set of coordinates. So basically we start with our center point, and then the first points we're going to look at these 4 points that surround it. So that's what we start with. So the main while loop here, this is what basically is doing all of the work inside here. So that's only it's like 45 lines of code, something like that. So basically you're going to see this concept in here, entropy. So don't worry too much. The word entropy is scary. It's not complicated. I'll explain it in a second. But basically what we're going to do is we're going to take a look at all of the points that we have in our candidates list, and we're going to try and figure out how many possible states can each of those occupy based on what points are already around them. So for our first point, we're going to take a look. So we have our center point. So let's say we take a look at the first point to the north of it. We're going to look at that, and we're going to say, hey, what's below me, directly below me? It's a crossroads. Okay, and then what's above me, to the left and to the right? And you're going to say that, well, there's nothing to above. There's nothing above me. There's nothing to the left, nothing to the right. So at this point, the possibilities I have are much bigger, because the only constraint that I have on what I can be is the fact that I need to connect to the crossroads below me. So I know that I need to have a vertical edge. So you can imagine, well, that means I could probably be one of these guys, or I could be a junction going to the right. I could be a junction going to the left, or I could be another crossroad. So I've got a lot of different possibilities. So this function, possible states, basically goes through and looks at all my neighbors around me and figures out what other things can I possibly have connected to me based on the maximum number of, or based on the whole set of all the edges that we have. So we get that passed in here. This all comes from the config, and you can see we check what neighbors are valid, and then we build up a set, and then we get this thing that we return, which is the possible nodes. So obviously, the more nodes are populated around you, the smaller that set becomes. So at the start you're going to have more, and then as the grid fills out, the possible states are going to reduce. So the goal of the algorithm is, so we look at all of our candidate sets, which we have here, we figure out how many states they have, and then we figure out the entropy. So in this case, the entropy is just going to be basically the number of states. So if there's 10 possible tiles that I could be, my entropy is going to be 10. If there's only 2, my entropy is going to be 2, and so on and so forth. So we do this for all of our candidates, and we record the lowest entropy that we find. And what we do is, if we find that there's 2 states, or any candidate that has the same entropy, and if it also is the lowest entropy, we hold them in a list. So basically, if we look around at all of a bunch of points and we say, hey, all these points are equally as low entropy, we're going to take them all, and then the next step is we're going to randomly choose one of them. And then at that point, we will collapse that probability state. So this is where the physics analogy comes into it. The whole idea of the wave function collapsing is that, well, so in physics you have wave functions which are defined by a probability density function, and then you don't know. This me badly trying to explain quantum physics off the cuff, but you're going to have, so you don't know its position, you don't know its velocity. You want to make a measurement really certain about that. So what you have to do, it's described as a wave, then it collapses, and then the probability collapsing means that you now know where it is, or whatever, how fast it's going, something like that. And then that is called wave function collapse in physics. So the idea here is that, well, I'm in a probability state. This thing can have multiple different states. I don't know which one it's going to be. I'm going to collapse it and choose its actual state. Hence the name. Anyway, that's where it comes from. So we're going to pick the one that has the lowest entropy, or ones that have the lowest entropy. We're going to randomly select one of them, the ones that has the lowest entropy. And then we're going to do another random selection, which is, of all of its possible potential states, we're going to randomly choose one. So any of the valid states that it could be, so it could be 2, it could be 3, it could be 4, we're going to just choose one of them because they're all equally as valid. So we're going to randomly pick one. And then in this case, this is where my weighting comes in. So if we have multiple valid states, I've applied this weight in here with this choose weighted function, which will then alter what that weight can be. So in my case, I've made it way more likely that we're going to have empty grass space, because I think it happens to look nicer in this specific map if the map looks more sparse. So we choose our state. We now insert this point into the grid along with the state that we chose. We then remove the point from the candidates because it's now picked. We absolutely know what the state is. It's collapse, so we know what it is. And then we have to take a look at that point, look at all of its neighbors. If it has a neighbor that hasn't yet found its way into the grid, so hasn't been collapsed, we add that into the candidates list. And then basically that's the end of this iteration of the function. And we scroll back up here and we start again, and we keep going until we've exhausted all of our candidates, basically. There was a little bit here at the end, which I skipped over, which was just, this is just image stuff. It's not super relevant to the algorithm. It just is how I then take a snapshot of the grid at that point and then save a frame of the GIF. And this is how our GIF will show us how this algorithm propagates. So with all that said, let's have a look at this algorithm. Let's have a look at the output of it. So here's a GIF that I prepared earlier. If I click here, you'll see it propagating. So we started from here at crossroads in the center, and you can see it now basically spiraling out the way as it fleshes out all of the unexplored states and decides what functions it's going to be, and you get this pattern. And you'll notice that it is completing full loops of the actual road network. So you see you've got some unconnected ones here, like this random square that doesn't connect anything, which seems a bit odd. And same here, this one doesn't connect anything, but it obeys all the rules. Remember what I said earlier is that there's no real complexity to this that we've introduced. It's quite simple. It's just, are these adjacently allowed to be beside each other? Yes, cool, then here you go, stick it into the map, and that's then how it'll generate. You can make other rules. You could make it so that you could try and enforce it so that the roads had to be continuous. You couldn't just have these like islands. But yeah, this is basically the crux of the whole thing. So I can run this really quickly just to give you an idea. This is also something kind of cool. So you can see if I go cargo run -- release, and it's running. It takes a little bit of time. There we go. So it outputs this too, which is cool, kind of ASCII version of the same grid. So this is the final grid that it looks like. And my GIF has been overridden with a new GIF. And there you go. You're seeing this is a completely different road network now. And every time you run this, you'll get a totally different network out of it, which is basically completely generated at random. Obviously, somewhat pseudo-random because of our rand function, but as random as that rand function can be is how random you're getting this map generated. Okay. I don't think I have anything else to add to this. I think that's pretty much all I really wanted to talk about. As I said, I did this just because I've seen this algorithm talked about before and seen it implemented and never actually done it myself. I was sick for the last couple of weeks and I was kind of feeling a bit low and wanted to tickle my brain with something that wasn't going to be terribly taxing. So I decided to mess around with this algorithm and do a little bit of image stuff, which is always kind of tickles my brain in a fun way. It actually did turn out to be a little bit complicated as I thought through it. My sick brain did not enjoy it terribly. I will admit that. But anyway, here's what we have. We have an algorithm. We have an explanation of it. I hope I've explained it well. I hope it makes sense. As always, the code is available on my GitHub, github.com/carey3. You'll find the repository is just called Wavefunction Collapse. I will throw a link to that in the description. And I think we're going to leave it here for this video. So thank you very much for watching, especially if you managed to make it the whole way along. And yeah, I will see you guys in the next one. Bye-bye.